Next big aspect for acid-base, and this is particularly true for a metabolic acidosis, is something called the plasma anion gap. All right, if I take my major cation, sodium, and I look at how much sodium there is, and then I take my two major anions and add them together. Notice in the graph, in the little bar chart, chloride and bicarb, I put them together. When we sum these two, they're still not the same level as sodium. So in other words, sodium is still higher than the sum of bicarb and chloride. This is called the plasma anion gap. Now, there's not truly an anion gap there. It's just standard blood sample gives me sodium, chloride, and bicarb. There are things out there that have negative charge. We're just not measuring them. So the plasma anion gap is simply sodium minus the sum of chloride plus bicarb. Now, if we remember our normal values, then we can always remember the normal plasma anion gap. Normal sodium is 140, chloride is 104, bicarb is 24. So I take sodium 140, chloride 104, add bicarb to it. 104 plus 24 gives me 128. 140 minus 128 gives me a plasma anion gap of 12 plus or minus 2. These are the normal values. However, you can sometimes see slightly different chloride levels, so pay attention to that. And some people also add in potassium, and so that will change what you expect to have for a normal plasma anion gap. In the U.S., most people don't utilize potassium, and I wouldn't worry about potassium on USMLE Step 1. All right, what elevates the anion gap? Well, mud piles do. Hey, a little mnemonic for you. Mud piles is M, methanol, U, uremia, which really just means kidney failure. D is diabetic ketoacidosis. P is peraldehyde. I is iron or isoniazid, which is an anti-tuberculosis compound or drug. L is lactic acidosis. E, ethylene glycol ethanol ketoacidosis. S is for salicylates, starvation ketoacidosis, and sepsis. So if the patient has a metabolic acidosis and the anion gap, again, anion gap is sodium minus the sum of chloride plus bicarb. If that's elevated, greater than 12 plus or minus 2, then you have an elevated gap metabolic acidosis. It's one of these mud piles. And I wouldn't worry too much about seeing P or I on mud piles showing up on USMLE Step 1. If the anion gap is normal, then you're hard up. Yeah, H is hypochloremia, often occurs with parental nutrition. A stands for acetazolamide, which is just really means any carbonic anhydrase inhibitor. Not just acetazolamide, any carbonic anhydrase inhibitor. R is renal tubular acidosis. D is diarrhea. And the last two I wouldn't worry about for Step 1, maybe Step 2. But I really wouldn't worry about ureteral diversion or pancreatic fistula on Step 1. But nonetheless, that's what the UP stands for. So again, if you have a metabolic acidosis, if the anion gap is elevated, do not pick diarrhea on the exam because diarrhea will be wrong. If the anion gap is normal, diarrhea could be a cause. Don't pick lactic acidosis if you have a normal anion gap. So, normal anion gap, you're hard up. If it's elevated, then think mud pile. All right, let's review. Let's review our 3 steps, and we've created here a little acid-base decision tree for you. All right, question number 1, what is deosis? If pH is low, then you have an acidosis. If it's elevated, then you have an alkalosis. And if you have the 2014 version of our book, we accidentally, under alkalosis in the parentheses, we said acidosis where it should say alkalosis. So that's what the little asterisk is for. Do apologize for that typo. So question number 1, what is deosis? Question number 2, what do we look at to determine the cause? The cause of the osis, bicarb. So I have an acidosis with elevated base. I have an acidosis with elevated base. That makes no sense. Huh? That makes no sense. How can you have an acidosis with elevated base? Oh, it's that respiratory thing. So I know it's a respiratory acidosis. Next, I have to determine if it's acute or chronic. And those are my ratios to determine if it's acute or chronic. And again, I'm just using 0.4. Technically, for chronic, it's 0.35. If I have an acidosis and bicarb is low, I say, well, that makes sense. Therefore, it's metabolic. Now I must compute what PCO2 should be. And I use Winters for that, 1.5 times bicarb plus 8. On the alkalosis side, so I have an alkalosis. To determine the cause, I look at bicarb. If bicarb is low, I go, huh? What? What? How can I have an alkalosis with low base? That makes no sense. How can you? Oh, it's that respiratory thing. So I know it's a respiratory alkalosis. Now I have to determine if it's acute or chronic. 1 to 0.2, 1 to 0.5 ratio. If I look at that bicarb and it's elevated, alkalosis, too much base, alkalosis, too much, well, that makes sense. It's metabolic. Now I must compute what PCO2 should be. Okay, and this is our Summers equation. PCO2 is going to increase 0.7 for every 1 milliequivalent increase in bicarb. 3 things just to note. Remember that CO2 goes up in a respiratory acidosis, and there's a compensatory increase in a metabolic alkalosis. That's Summers' equation. PCO2 goes down in a respiratory alkalosis because I'm blowing off CO2, but there's a compensatory drop in a metabolic acidosis, Winters' equation. Don't forget to calculate the anion gap. All right, utilize this decision tree. It just takes you 1, 2, 3. After question 2, notice where you are on this decision tree. You are at the primary disturbance, either metabolic or respiratory acidosis, or metabolic or respiratory alkalosis. This decision tree then takes you directly right to what calculation you need to make. So just follow the decision tree. Do 1, 2, 3. 1, 2, 3. And after you've worked with this a few times, it'll just be ingrained and it'll just, oh, you'll have silly fun. You'll have silly fun. Let's have silly fun diagnosing acid base. Okay? Diagnosing acid-base disturbance from ABGs. It's silly fun. All right, what I want you to do is look at this slide. Don't look at your book. What I want you to do is try to answer it. So stop the video, answer it, and then turn the video back on, and I will go through the answer. All right, what do we do? Same 3, always. pH is 7.3. What is the osis? Well, I have an acidosis because it's low. Question number 2, what's the cause? I look at bicarb. Well, I have a metabolic acidosis because bicarb is low. So, question 1, pH low, acidosis. Question 2, cause, bicarb is low. Acidosis, low base, makes sense, it's metabolic. Now, if I have a metabolic acidosis, I need to see if CO2 is where it should be. I calculate that using Winters' equation. Patient has a bicarb of 14. 14 times 1.5 is 21, plus 8 is 29. Patient has a CO2 of 30. So this is a metabolic acidosis with a respiratory compensation. CO2 is within the range of what it should be. Remember, Winters determines what it should be. All right, question number 1, what is the osis? Hopefully you stop the video and then come back for all of these. What is the osis? I look at pH. pH is elevated, so I know I have an alkalosis. I then look at bicarb, and I see that bicarb is low, so I have an alkalosis with too little base. Huh? Oh, it's respiratory. It's respiratory. Now I have to determine, is this acute or chronic? If acute, patient has a PCO2 of 20, just 20 below normal. So 20 times 0.2 is 4. So bicarb will be 20 if it's an acute respiratory alkalosis. And I usually just calculate the acute first and then look at it. If I have to, then I calculate the chronic. And here, I don't need to calculate the chronic because my acute number is right on what the patient has. All right, if it were chronic, let's just do a practice calculation. 20 times 0.5 is 10, so bicarb will be around 14. Technically, but the lower limit for bicarb is 15, but we utilize this 14 because just for illustrative purposes. But really, bicarb won't get below 15. So, final answer here is an acute respiratory alkalosis. Again, please stop the video and give this a try yourself. I'm going to go ahead and move forward. All right, I'm doing the same 3 steps every single time. Question number 1, what is the osis? Well, I look at pH and it's low, acidosis. I then look at the bicarb and it's elevated, and I say an acidosis with too much base. What? Oh, yeah, it's that CO2 thing. It's a respiratory problem. So I have a respiratory acidosis. I now need to determine, is it acute or chronic? If acute, then bicarb will be 28. How do I know that? Because CO2 is 40 above normal. 40 times 0.1 is 4. So bicarbonate will be 4 above the normal of 24. 24 plus 4 is 28. If it's chronic, then bicarb will be 40. How did we get that? 40 times 0.4 is 16. So 24 plus 16 is 40. Hey, let's just try it real quick with the technically correct number. Notice, if I use 0.35, I can't do that quite as quickly in my head as I can 0.4. But bicarb will be elevated 14, so bicarb will be 38. The patient has 30. And remember, this is a really high CO2. It's doubled. So you can see it really makes no difference if I use 0.4 or 0.35. I'm going to come to the same answer. So it's much closer to the acute level, so this is an acute respiratory acidosis. Again, stop the video, try it on your own, then restart it. Question number 1, what is the osis? The osis is elevated. So we have an alkalosis. Next, I look at bicarb. So I have an elevated pH with an elevated bicarb. That makes perfect sense. This is metabolic. Now I have to determine, did they compensate? Did CO2 compensate appropriately? What should it be? Well, here's where we use Summers' equation. PCO2 is going to go up 0.7 for every 1 milliequivalent increase in bicarb. Well, bicarb's 44. That's 20 above normal. So 20 times 0.7 gives me 14, plus 40 is 54. Patient has 52, so it's within 2. Remember, I'll go 2 either side. So this is a metabolic alkalosis with a respiratory compensation. Hey, wait, we can't do this one. There's no pH. How are we going to? Oh, we can do it. Watch. Bicarb is 20. PCO2 is 55. But that's a low bicarb. So I know immediately this is a metabolic acidosis or a respiratory alkalosis. Those are the 2 conditions in which bicarb goes down. Either metabolic acidosis or respiratory alkalosis. I look at that CO2 and it's 55. Oh, well, this is clearly a respiratory acidosis on top of a metabolic acidosis. Remember, if CO2 and bicarb go in opposite directions, notice bicarb went down, CO2 went up. This is a mixed disturbance. So my final answer is a mixed metabolic and respiratory acidosis. Here, if we don't pay attention to the bicarb, here's where we could miss the metabolic acidosis that exists here. We clearly have a respiratory acidosis, But we also have a metabolic acidosis, and we know that because bicarb went down. If this were a pure respiratory acidosis, bicarb would not have gone down. Remember, it would go up. All right, next aspect for acid-base is the Davenport plot. And all we're going to do is plot what we just discussed. That's it. And we utilize the Davenport to help facilitate our understanding of what we just discussed. And also, if you're going to see a graphical representation on USMLE Step 1 related to acid-base, then it's most likely going to be a Davenport. So that's why we will talk about Davenport. My gold standard pH is 7.4. Gold standard PCO2 is 40. Gold standard bicarb is 24. So as you can see, that circle and near the middle of that graph, those are my gold standards. That's where we always start because that's gold standard. pH 7.4, PCO2 40, bicarb of 24. All right, first question we ask, what is the osis? So on the Davenport, if we're on the left of the green line, then we have an acidosis. To the right, alkalosis. That's question number 1. All right, question number 2 deals with the cause of the osis. Now, on a Davenport, what's it going to look like when I change CO2? Again, follow the chemical reaction. We've already discussed this idea, but just go through the chemical reaction. This would represent a PCO2 of about 60. The next dot would represent a PCO2 of about 80. Remember, when I increase CO2, pH falls because CO2 is an acid, and bicarb goes up. We even quantitated how much bicarb went up. It goes up 1 to 0.1 ratio. That's where the 1 to 0.1 ratio goes. Now, in a Davenport, we don't have to be quantitative. So we really don't have to quantitate it. But the point is, as CO2 goes up, pH falls, so we move to the left, but bicarb goes up. Notice that the bicarbonate went up. In a alkalosis, respiratory alkalosis, if I drop CO2, then pH goes up and bicarb falls. How much? 1 to 0.2 ratio. Again, you don't have to worry about being quantitative here on the Davenport, but the point is, we can just show the buffer line. This buffer line represents the changes in bicarb and hydrogen when I change CO2. So this purple line represents effectively the respiratory buffer line. Moving up and to the left represents increases in CO2. Moving down and to the right represents decreases in CO2. All right, now let's change hydrogen. Okay, let's change hydrogen. Now, if I add hydrogen, pH goes down, drive the reaction to the left, and bicarb falls. So, increasing hydrogen decreases pH and bicarb, somewhat like this. Going the other direction, if I decrease hydrogen, that will increase bicarb and increase pH. So that's the relationship. And again, we don't have to be persnickety. We don't have to be, exact. We're just going in general directions here. So we could connect all of these dots. And in all of these dots, for right now, I haven't changed CO2. Remember, CO2 increasing means up and to the left, decreasing down and to the right. So I'm not changing CO2. I'm just drawing the metabolic buffer line that the body will follow if I change hydrogen. Acidosis, down and to the left, alkalosis, up and to the right. So this metabolic buffer line is also called a PCO2 isobar because CO2 hasn't changed. These are metabolic changes with no change in CO2. So here's my respiratory buffer line. Here's my metabolic buffer line. Note that these buffer lines now kind of slice up the Davenport, kind of like a pizza. In the upper left, we have a respiratory acidosis. So any dot moving from our center dot that goes into the upper left quadrant is a respiratory acidosis. If it goes into the lower left quadrant, it's a metabolic acidosis. If it goes into the upper right quadrant, then it's a metabolic alkalosis. If it goes into the lower right quadrant, then it's a respiratory alkalosis. Notice how we've just split it up. Okay, and this is the same as question number 2. What is the cause of the osis? So we're looking for dots where the patient is. Upper left, respiratory acidosis. Lower left, metabolic acidosis. Upper right, metabolic alkalosis. Lower right, respiratory alkalosis. Again, we're going in direction. We don't have to be persnickety with quantification or to quantitate it real persnicketively. All right, the next question then becomes compensation, right? Question number 3 is compensation. All right, let's move along, follow the red arrow. We've moved along the respiratory buffer line. We have an increased CO2, which dropped pH and increased bicarb. This is an acute respiratory acidosis. Now, for compensation on a Davenport, here's all you do. You just mentally imagine, how do I get back to the green line? But I have to follow a buffer line. I must follow a buffer line. So I've moved up and to the left. Now I want to get back to the green line. Visually, how am I going to do this? Stop the video if this doesn't resonate. This is the only direction you can go to get back to the green line and follow a buffer line. Remember, I can't come back down the respiratory buffer line because that's my fundamental problem. So the only direction I have, the only way I can get back toward the green line is to go where I've drawn the second red arrow. Now, notice what happened to bicarbonate. Bicarbonate went up, which is exactly what we discussed. If you have a respiratory acidosis, the kidney is going to add bicarbonate to the system. So we're going to increase bicarb. So we move along that buffer line, the metabolic buffer line, but notice we have generated a new higher respiratory buffer line. We added bicarbonate to the system. How much? 1 to 0.4. Again, you don't have to quantitate it here on the Davenport. You just have to see, did we create a new respiratory buffer line? Did we move? Did the circle? Question on the exam, did the patient move to a new higher respiratory buffer line? If they did, then it's a chronic respiratory acidosis. If you don't, then it's acute respiratory acidosis. And again, acute respiratory acidosis we can call uncompensated respiratory acidosis. Chronic respiratory acidosis we can call compensated respiratory acidosis. Going the opposite direction, this represents an acute respiratory alkalosis. We're moving along the respiratory buffer line to a higher pH and a lower bicarb. So this is an acute disturbance. What does the kidney do? It gets rid of bicarb. How much? At a 1 to 0.5 ratio. Again, you don't have to quantitate here, but the point is, for compensations for a respiratory disturbance on the Davenport, is whether or not the patient moved to a new respiratory buffer line. In other words, if a new respiratory buffer line was created. And a new buffer line is created by the kidneys either hanging on to bicarb, respiratory acidosis, or getting rid of bicarb, respiratory alkalosis. So, to repeat for respiratory alkalosis, if I stay on the respiratory buffer line, it's an acute or uncompensated respiratory alkalosis. If I move to a new respiratory buffer line, then it is a chronic or compensated respiratory alkalosis. All right, let's talk about compensations for metabolic disturbances. This would represent a metabolic acidosis. Remember, the lungs are going to kick in and we're going to drive down CO2. Again, we're moving toward the green line, where you go down the metabolic buffer line. I want to come back to the green line. So the arrow, the second arrow that's moving down and to the right, represents a decrease in CO2. That is the compensation for metabolic acidosis is for the lungs to drive down CO2. Quantitatively, we calculate what CO2 should be using Winters. We won't have to do that calculation with the Davenport. We just have to see, did we change the level of CO2? And in this example, we did. This would represent a metabolic alkalosis. The respiratory response is to try to get us back to the green line. What happened to CO2? It went up. That is the compensatory response to a metabolic alkalosis. Again, if we move off a buffer line toward the green line, then for the Davenport, we call it compensation. Now, stop and think for a moment. If I moved in this direction, the last arrow I drew in, what would that represent? Correct. That is a mixed metabolic and respiratory acidosis. Notice that CO2 has gone up and we have a low bicarb. They've gone in opposite directions. We're not moving toward the green line, we're moving away from it, so it's a mixed disturbance. Similarly, what would this represent? Correct. This is a mixed metabolic and respiratory alkalosis. We have a metabolic alkalosis, we're in the upper right, and CO2 went down instead of going up. So that's a respiratory alkalosis. So this is a mixed metabolic and respiratory alkalosis. Notice that CO2 and bicarb are going in opposite directions. All right, let's try some without you looking at the book for right now. And if you have to stop the video, then do so. Okay, after I show each letter. So we'll start with A. What does A represent? Well, this is an acute, uncompensated respiratory acidosis. Remember to give it the full description. You can't just say respiratory acidosis. You have to say acute respiratory acidosis, or you could say uncompensated respiratory acidosis. B, remember, complete answer. Notice we have moved off the normal buffer line, the normal respiratory buffer line, but we still have a respiratory acidosis. So this is a chronic respiratory acidosis. We have shifted the respiratory buffer line. We have added bicarbonate to the system. That's what the kidneys do. This is a chronic or compensated respiratory acidosis. What does E represent? E is a metabolic alkalosis with a respiratory compensation. What does G represent? Well, G is a metabolic acidosis with a respiratory compensation. What does I represent? This is an acute respiratory alkalosis. What does J represent? Notice we still have a respiratory alkalosis. We have a respiratory alkalosis, but we're no longer on the normal respiratory buffer line. We have moved toward the green line. So this is a chronic respiratory alkalosis, or you could also call it a compensated respiratory alkalosis. Not in your book, but try that one. Yes, this is a mixed metabolic and respiratory acidosis. We're in the lower left quadrant, so it's a metabolic acidosis, but CO2 has gone up. Bicarb's gone down, CO2's gone up. They've gone opposite directions. It's a mixed disturbance. Another one not in your book, but try this one. Yes, a mixed metabolic and respiratory alkalosis. We're in the upper right quadrant, so we know it's a metabolic alkalosis. CO2 should have gone toward E. It didn't. It went the opposite direction. So bicarb and CO2 are going in opposite directions. This is a mixed metabolic and respiratory alkalosis. This acid-base is silly fun. Notice how the Davenport is just reiterating what we already discussed. It's just a graphical representation.